Good morning, students. In our last class, what we have seen is electric flux density. And what do you mean by electric flux, right? So what is electric flux? Let us recall what we have studied in the previous session. What is electric flux? So the number of flux lines is equivalent to the charge present in that particular area is called as flux lines. What is flux density? So electric flux density is defined as the number of flux lines passed through the closed surface, so which is kept normal to the direction of flux lines, is called as flux density. That is what we have derived the mathematical model. D is equal to epsilon naught into E, where E is the electric field intensity, right? So the flux density direction and electric field intensity direction and unit vector direction, both are, all the three components are in the same fashion, right? So that is what we have seen in the previous class. By using those concepts, those dot product, what is the dot product we have seen? So d psi is equal to d dot ds, right? Where ds is the unit surface area where ds is given by n cap into ds, where n cap is the normal vector which ejects from the surface, right? That is what we have seen in the previous class. So by using those concepts, let us define what is Gauss law. What do you mean by Gauss law? See, the statement says that the total flux or displacement through any closed surface is equal to the total charge within the surface regardless of how the charges are distributed, and the contribution to the said flux from the charges outside the surface is zero. So we need to consider all these considerations. Okay, so let us read once again. The total flux or displacement. What is this displacement? You have not seen this. So electric flux is also called as electrical displacement. Electrical displacement. The another name for electric flux is electrical displacement. That is why we have mentioned displacement here. Okay, so through any closed surface, within the any closed surface, the total electric flux or electrical displacement is equal to the charge within the closed surface, charge which is present inside the closed surface regardless of the how the charges are distributed. Charges may be a continuous charge distribution or a unit point charge, whatever, the line charge distribution, anything you can consider. But the total electric flux is equivalent to the number of charge within that closed surface. And one more thing you need to see here at the last sentence, the contribution to this said flux, the contribution to this total flux from the charges outside the surface is zero. So the contribution to the flux generated within that closed surface from the outside charges is negligible and it is equivalent to zero. So we need not to consider that charges which is present outside the surface area. So these are the three important things you need to remember while writing Gauss law. This is the mathematical model we need to derive for Gauss law, where D is the, what is D? Electric flux density. What is ds? Unit surface area vector is equal to Q. What is Q? So Q is the charge present within that closed surface area. See, the total flux density within the closed surface is equivalent to charge present within that closed surface area. This is what the Gauss law says, that is the statement. Okay, we need to derive this. What is this symbol states? This is the surface integral, closed surface integral of d dot ds, right? So we need to derive this mathematical model for Gauss law by using electric flux density equations and electric field intensity equations. Okay, in order to do that, let us have a geometrical model. Let us consider a point charge. Let us consider a point charge Q at point O. Let us consider a point charge Q at point O. Okay, let us have an arbitrary surface around this point charge Q. What is this? An arbitrary surface around the point charge Q. Okay, let us consider an elementary surface area. Let us consider an elementary surface area which is named as ds within this closed surface. What is this? Elementary surface area within this closed surface, okay, which is named as ds. Let us have point P which is at a distance r from the origin O. Let us have point P on this elementary surface area which is at a distance r from point charge. Okay. Now, this vector is acting along the line OP, then A cap r is the unit vector, where A cap r is the unit vector acting along the line O to P. Then the electric field intensity also acting along this line. We know that unit vector and electric field intensity both are in the same direction. Also we know that the electric flux density D also acting along the same line. Therefore D is also acting along this line. Okay. Now in the previous session what we have seen, so electric flux density says that the number of flux lines passed through the closed surface area which is kept normal to the direction of fluxes. But here the direction of this electric flux density, flux line D, is not normal to this surface area ds, because this is an arbitrary shape which is not normal. Under that circumstance, what we need to take, in the previous class I have explained, we need to consider a unit normal vector n cap. Under this circumstance, when the flux line is not normal, when the surface is not normal to the surface flux lines, so we need to consider a unit normal vector which is erect normal to this elementary surface ds, which forms an angle theta between D and n cap, This is the geometrical consideration we need to consider. Okay, so this elementary surface area ds forms the solid angle d omega, which forms the solid angle d omega at point O. Okay, so which is called as solid angle. Why it is called as solid angle? We are considering three-dimensional cone shaped area. That's why d omega is the solid angle formed at point O due to the elementary surface ds. Let me explain this geometry once again. Let us consider a point charge Q, okay, and consider an arbitrary area around it, arbitrary surface area around it, and consider one more elementary surface area within that arbitrary shape, okay, so which is called as ds, and let P be the point on this elementary surface area which is kept at distance r from O, okay, which is kept at distance r from O. Unit vector, flux density and electric field intensity all are acting along the line O to P. Okay, this is what the direction. Since this area is not normal to the flux lines, so we need to consider an elementary vector n cap which ejects normal to this area, elementary area, which forms an angle theta between D, electric flux density. So which forms an angle theta between D and n cap. So how to obtain the electric flux out of this elementary surface ds? So the electric flux due to this elementary surface ds is d psi. Psi is the symbol which we have used, right? D psi is the electric flux generated by this elementary surface ds. So which is obtained by using the dot product of d dot ds, which is obtained by taking dot product between d and ds, right? What is ds? Where ds is equal to n cap into ds. So this is what we have written in the previous session. So let us recall the same thing. Okay. So these two equations have been already written while explaining electric flux density, right? So same equations we have seen. And one more thing you need to remember. So a dot product between any two vectors A and B is equal to magnitude of A into magnitude of B into cos theta. This is the dot product equation, right? Okay. Now, so these two equations you need to remember. Now proceed with this. In order to obtain electric flux density within this elementary surface ds and within the overall surface which we have considered arbitrarily is obtained by psi is equal to surface integral of d psi. So this is what we need to do. What is d psi? Integration d dot ds. We need to integrate for the entire closed surface area in order to obtain total flux. See, we need to consider the total flux, right? So we don't want elementary flux through the elementary surface. We need to have the total flux within this closed surface area. So we need to integrate all the flux densities contributed by each of the elementary surfaces. Okay, that's why we need to integrate surface integral of d psi in order to obtain total flux. Now coming back to this, according to Coulombs law states that electric field intensity E is equal to Q divided by 4 pi epsilon naught into R square into A cap R. Okay, name this as equation 1. According to Coulombs law, electric field intensity is given by E is equal to Q divided by 4 pi epsilon naught into R square. What is D? D is equal to epsilon naught into E. Electric flux density is equal to epsilon naught times of E, relationship between electric field intensity and electric flux density, which we have seen in the previous class, which is given by Q divided by 4 pi R square into A cap R. Let it be equation 2. Okay. Now the agenda is to calculate d psi, then integrate all the d psi's in order to obtain total flux, right? So d psi is equal to d dot ds. What is d? Q divided by 4 pi R square into A cap R dot. So we are considering dot product. What is ds? ds is equal to n cap into ds, right? So this is the equation. So what is this? A cap R unit vector. What is this? N cap unit vector. Dot product between these two vectors we need to consider. See, dot product between any two vector is equal to magnitude of these two vectors into cos theta. What is the magnitude of A cap R? Now we need to calculate the dot product of A cap R dot N cap. What is the magnitude of A cap R? 1. What is the magnitude of n cap? It is also 1 into cos theta. Therefore, A cap R dot n cap is equivalent to cos theta. Therefore, the equation d psi becomes Q divided by 4 pi R square into cos theta into ds. So this quantity is replaced by cos theta here. Got it? So this is the dot product between A cap R and n cap. So cos theta. Now in order to obtain psi, we need to integrate within this closed surface. We need to integrate all the d psi components. Therefore psi is equal to surface integral of Q divided by 4 pi r square into cos theta into ds. Got it? Rearranging this equation gives psi is equal to, so take the constant outside, q divided by 4 pi is taken outside, surface integral of ds into cos theta divided by r square. Okay, this is the equation. What is this? ds into cos theta divided by r square is called as solid angle, where ds into cos theta divided by r square is the solid angle formed due to the surface ds at point O. Okay, this is called solid angle. Therefore, equation for psi becomes q divided by 4 pi surface integral of d omega. So name this as equation 3. Okay, this is equivalent to this form, where d omega is the solid angle formed at point O due to the elementary surface area ds. Got it? So this is what we have got. Now how to solve this equation? Now we need to have the analytical geometrical formula for this. According to that, any solid angle within this closed surface at any point is equal to 4 pi. The solid angle within the closed surface at any point due to the surface area is equal to 4 pi only, always. Okay, according to that, so surface integral of d omega is equal to 4 pi because at any closed surface total solid angle within surface at any point is equal to 4 pi only. According to this assumption, surface integral of d omega is equal to 4 pi. Substituting that, then psi is equal to q divided by 4 pi into 4 pi. 4 pi get cancelled, psi is equal to q. This is the result what we are expecting. According to the statement, the total electric flux or electrical displacement through any closed surface is equal to the number of charges associated with it. According to the statement, the same thing what we have got mathematically here. So this is what I said in the very first class. We need to analyze all this electromagnetic wave behavior mathematically. So Gauss law says that the total flux produced by a closed surface, by a charged closed surface, is equal to the number of charges associated with it. According to the statement, so mathematically we are supporting it. See, the total flux psi is equal to q. That means psi is the total flux produced due to this closed surface, charged closed surface, which is equal to the number of charges associated with it. Number of charge present within the closed surface. In the last sentence what we said, any charge which is outside this closed surface contributes 0 to the electric flux density. Okay, therefore this charge must be enclosed within this closed surface. Okay, keep that in our mind. Now this is what we have got. What is psi? According to this equation, psi is integration of d psi. Okay, so it can also be written as surface integral of d dot ds is equal to q. While writing statement, the Gauss law is written in this form. Surface integral of d dot ds is equal to q. See, psi is equal to q, which we have got. What is psi? Surface integral of d psi. D psi means d dot ds. Therefore, surface integral of d dot ds is equal to q. After deducing all these equations, we have obtained the required form of Gauss law. So you need to remember, electric flux density is also equivalent to electrical displacement, which is given by Gauss law. Gauss law mathematically written in this form. So this is the mathematical arrangement for that. Understood? Continuing with the derivation. So we have derived the mathematical model for Gauss law, that is surface integral of d dot ds is equal to q. This is what the derivation tells. Now we need to analyze this Gauss law for 3 different cases. Case number 1 says that when many point charges are available in the closed surface. This is the first case. Case number 2 says that when continuous distribution of charges are available in the closed surface. Case number 3, when no charges are available in the closed surface. We need to analyze this Gauss law for 3 different cases, 3 different special considerations. See, so while deriving this Gauss law, what we have taken geometrically, we have considered a point charge, a single point charge q, and we have taken the arbitrary surface around it, right? So when many point charges are available within the closed surface, what will happen? So n number of point charges are available inside a arbitrary closed surface. So under that circumstance, then total electric flux psi is equal to psi 1 plus psi 2 plus psi 3 and so on up to psi n. Which principle is that? Superposition principle. We have seen already. See, psi 1 is the electric flux contributed by point charge q1, psi 2 is the electric flux contributed by charge q2. Similarly, psi n is the electric flux contributed by nth point charge qn. Okay, summing all these things in order to obtain psi. This is how you need to calculate the electric flux. So, okay, by using n number of point charges within the closed surface. Therefore, this can also be written as q1 plus q2 plus q3 and so on up to qn. Therefore, psi is equal to summation of q. So this equation holds good. So summing all the charges in order to obtain total flux density within the closed surface when many point charges are available inside a closed surface. This equation holds good. You need to apply, simply remember, we need to apply superposition theorem. So when many point charges are available within the closed surface, so you need to remember, oh, it is superposition theorem problem, we need to apply that. Okay. Now coming to the second case, when continuous distribution of charges are available in the closed surface. We know that what do you mean by continuous distribution? Within the finite area, when many point charges, means infinite number of point charges. There is no space between 2 point charges, means infinite resolution, infinite number of point charges are available. Then the density varies from one point to another point. Consider this closed surface area. Okay, consider a closed surface area, arbitrary closed surface area. At some point the charges are densely packed. Charges are densely packed. At this area charges are lightly packed, and here so density varies from one point to another point. Under that circumstance, what we need to do? We need to consider charge density. See, when a closed surface area is having different charge densities within it, we need to consider the charge density component in order to have the equation for continuous distribution of charges. Got it? Then under that circumstance, integration of rho v into dv we need to consider. Okay, so what is rho v? Rho v is the charge density, which varies from one point to another point within the closed surface area. Okay, that is what I have written. Rho v varies from one point to another point within the closed surface area. Why it is continuous? So there is negligible distance between 2 point charges. That means we can say, in other words, infinite resolution, infinite number of charges present within the closed surface. Okay, under this circumstance, the Gauss law can be written as surface integral of d dot ds is equal to q, where q can be evaluated as surface integral of d dot ds is equal to volume integral of rho v into dv. For continuous distribution of charges within the closed surface, then Gauss law can be written in this format. Got it? Then coming to the third case, when no charges are available in the closed surface. So remember the statement in the last sentence, what they have said. The contribution from the charges present outside the closed surface area is 0. The contribution of charges outside the closed surface area is 0. Therefore, no contribution to the flux from the charges located outside the closed surface. Hence, Gauss law d dot ds is equal to 0. This is the result for the charges which is present outside the closed surface area. These are the three special considerations, special cases for Gauss law. You need to remember. So first case is when many point charges are available within the closed surface area. For that you need to apply superposition theorem. For second case, when continuous distribution of charges are available within the closed surface area, you need to consider charge density to define Q. So according to that, so Gauss law can be rewritten in this form. Third case is that when charges are present outside the closed surface, then the contribution is absolutely 0, then the Gauss law is equivalent to 0. Okay? Thank you.